Hello everyone, today we are going to be like Priyadarshini from IIT Kanpur and we will tell us about our work on tensionless strings.
Yeah. So first I will begin my talk by thanking the group over here for giving me this wonderful opportunity to come here and talk about my work. So today I will be talking about both the closed and open sector of tensionless strings. So in the talk, I will present the results of basically these three works, which has been done with Arjun, Pranay, Sankhadi, Stefan, and Daniel recently, and two collaborators of mine, Aritra Banerjee and Vidya. I will also use for review few of the papers, which are these three, and some other references. So the plan of my talk will go as follows. So first of all, I will give a review of tensionless closed string, which will contain the classical as well as quantum aspect of it. Then I will explore until now unexplored the tensionless open strings. Then I will show how if we compactify one of the target spacetime, how does that affect the mass spectrum and duality? And if we generalize that to higher dimension compactification and introduce B field to it, how does this affect the duality? Then I'll give conclusion with some future. Okay, at some places I will be using some analogy from the string theory we have, but if it is not clear, we can try to discuss it. So I'll start with giving a brief review. String theory has been, we all know, has been the most promising framework for quantum theory of gravity over the past few decades. It generalizes the notion of point particle to one-dimensional string as the fundamental object. And for the non-interacting string, the only free parameter is the tension, which is related to the length of the string as length square in this line. So we can take two extreme limit of this tension. One could be the point particle limit, which is the low energy limit. And the other, which I will be mostly talking about here, is the extreme stringy limit. Extreme stringy, I'm saying, because here, since tension is zero, so length of the string is becoming very large. Or this is called the ultra high energy sector string. This tensionless sector of string theory was first analyzed by Stipe in 1977. Okay, so first of all, I will try to construct the tensionless strings, the action of the tensionless string, and then we will go as it has been done for string theory in the literature. So in order to construct the action, I will start from very known action of string theory, which is the number action. That is the tension, tau and sigma are the worldsheet coordinates, and gamma alpha beta the induced metric. X mu are the space-time coordinates. Now we need to construct an action which is for tensionless string. So at first glance, we will think that, okay, let us make this tension to zero. However, we can see here that taking tension to zero limit here will make the whole action vanish. So we cannot take the tension to zero here. So what we do, we follow the analogy of the massless limit we take for the relativistic point particle. So it is true. Yeah, so we start for massless point particle, the action is given as in equation 2. Here also you see we cannot take mass to zero. So what do we do? Since this is a constraint system, we solve this by Hamiltonian formalism, and we generally introduce some auxiliary field called ambient. So what we do, we introduce some field like this, and here you can see, so now the mass is not sitting outside, however it is inside, and we can take the masslessly. The same analogy we are going to follow for tension in order to construct the action for the tensionless string. So this was given for the tensionless string. This was given by Isberg and collaborator in 1994. What we do, we find out the generalized momenta. Then we find out the total Hamiltonian, which is the sum of these two constraints, where lambda and rho are the Lagrange multipliers. And using this, we can find out the action where you can see here the tension is now has gone to the inside, and we can take the tensionless limit here. And this action can also be written in the Polyakov form given in equation 5, where G alpha beta is identified as this. Here also you can see that we can take tensionless limit over because it is inside it. And how to take this tensionless limit is that we replace T of root of minus G alpha beta to V alpha V beta, which is rank 1 matrix, where V alpha and V beta are the vector densities given by this expression. Now, the implication of tensionless string on the worldsheet could be that this metric is becoming degenerate when we take the tensionless limit. Now, this can also be seen from the limiting analysis when we go from when we consider this ultra relativistic limit on the worldsheet, where when we take UR limit on the worldsheet, and that is tau goes to epsilon tau and sigma goes to sigma. So here the metric this cannot take, if we take this to 0, we cannot invert it. So what we do, it's fine. Now this is clear because it will be this. We get -1. And when we multiply epsilon square and define this metric, we get this, which is degenerate. So the degeneracy, what we are going to get on the worldsheet, can also be seen from the UR limit.
That I would have put the -1 over epsilon square 0, 0, 1, right? As just the inverse. Did you mean by eta alpha beta the inverse of that?
Yeah, now I have not put this to 0 now.
You know,
Just that is finite. So when we just invert it, we get this. This is.
Wouldn't you just invert epsilon square to 1 over epsilon square and 1 to 1? So you done something here.
Yes.
At times that was yeah. Maybe just inverted the.
Yeah, so this will be 1 by
1 by epsilon square, and then the second one would be 1.
Yeah, sorry.
Yeah, no, that's okay. Yeah.
So there will be silence.
And then you get that.
Yeah.
Yes, absolutely.
So I want to say this statement that this degeneracy structure on the worldsheet, because of the presence of this, because of this tensionless limit, it can also be seen from this.
Sorry, and what's going on with the rows and the lambdas?
We are going to fix them.
Right, but right now you haven't fixed any gauge.
No,
Okay.
nothing. Now, just now I am constructing the action. Then from the symmetries, I'll just gaze fix them, and then from the residual symmetry will come. I will explicitly say that. And the action which we are going to get is this, which is the tensionless action. I'm going to work on this particular action. Okay, so in coming 2-3 slides, I will be giving the roadmap of where am I going to start, that is from the string theory, where we know which we know, and where am I going to end this presentation. So that will be a bit technical, but I will explicitly explain when I go. Okay, so now we know what is tensile string theory, and it is given by the Polyakov action. I already showed you this is the IIT, all the authors, Isberg, Lindstrom, Sundberg, and Theoridis. So this is the tensionless action for the tensionless theory. This is the action for the tensile theory. Now in string theory, we have two kinds of objects, closed string and open string. They are different from each other by the boundary condition on sigma. The periodicity condition gives us the closed string, and the open string, we are going to get the Dirichlet and Neumann. However, when we go to tensionless theory, we will get one extra condition along with these two conditions. I will show them.
And just remind me, what was V alpha again? Sorry.
The vector densities.
Just once.
So what we are doing, we are just replacing this by
Yeah. Square root of 2. Lambda is just some constant.
lambda is the
Okay, it's a Lagrange. So you have to integrate over that also?
Yeah.
Just show once more, sorry, V alpha. Sorry. So, okay, you have this Lagrange 1 minus. Okay, thank you so much.
Yeah, so
we
where,
are going to fix rho as well as 2 0.
so where did the rest of the degrees of freedom of the metric go?
Sorry?
I thought lambda was also one of the degrees of freedom of the metric. So G is supposed to have 3 degrees of freedom, right?
G is supposed to have 3 degrees of freedom. Yeah.
So where are the rest of them?
Yeah. So since this is Y invariant.
So you use Y to fix something.
Yeah. So that will take care, V alpha V beta takes care of that invariance, and then later we will just fix 2 of them, which will be like V alpha to have the conformal
Which are the two? Rho and?
rho and lambda.
Oh, so the Lagrange multiplier becomes connected to a degree of freedom of the metric.
To some extent.
Okay.
I thought that you've just taken the t going to 0 limit in your first packet, right? That gives you this degenerate.
Yeah.
Is this correct?
Yeah.
Okay. So, I mean, I didn't understand the why fixing the base freedom is by something. I
Yeah,
thought this
so-
was just like take t going to 0.
Yeah. That is here. Taking the tension goes to 0 limit,
Okay,
and then we will get some action which is this.
correct, yes.
Now this action will have certain symmetries, which is the diffeomorphism invariance. And I'm saying that in string theory we have in the H alpha beta that goes to eta alpha beta because of fixing 2 things, the diffeomorphism as well as Y. So Y invariance can be is absorbed in this definition V alpha B beta on T root G.
Since the left hand side is already
Yeah.
You might as well scale it.
Yeah, but it's not like the most general while invariant metric can be written like that because, you know, V alpha, V beta is a very degenerate metric, right?
Yeah,
It has
yeah,
1-0
yeah,
elements.
yeah.
That's right.
Yeah.
So it's just that the metric becomes in this limit.
Yeah.
That makes sense.
Yeah.
Okay, so we started with tensiles, the action for tensile tensionless. We have closed and open strings. Now, the mode expansion of tensile and tensionless string, I've just displayed it, but I will explicitly prove this, how we are getting. And we are using this C0 and the Cn and Cn tilde in place of alpha n and alpha and tilde, the left moving and right moving. So for tension, just to make sure that for tensionless strings, I will
Growths are this ones, yeah? Yeah, but I'll get.
now, so since we have these boundary conditions, so those will put some constraint on the mode expansion. What kind of constraint? This closed string, since I showed you that this has this periodicity condition, so there will be no linear term in sigma over here if you want to study about closed string. So that way, in tensile also, for closed string, the constraints on mode expansion due to boundary condition is linear term in sigma balances. That is the case for both the tensile and tensionless. And for open string, in this talk, I will be particularly talking about Dirichlet condition, which connects the left moving and right moving modes. The same happens, we saw it explicitly, that the same happens for the open string as well. Now, residual symmetry algebra. Now, what do we mean by residual symmetry algebra? We have the action, we have its symmetries, gauge symmetries. Now, there is some redundancy in the system, so we fix the gauge. Now, since we fix the gauge, we get, and after fixing the gauge, the action again remains invariant under certain symmetry, which is called the residual symmetry. Okay? And this the generators of this residual symmetry will, in case of tensile theory, will give us 2 copies of Virasoro. For open string, it will give single copy of Virasoro. However, for closed string, it gives us BMS3 algebra or 2-dimensional conformal Carrollian algebra. When we go to open string, which has not been done yet, so this gave us the 2-dimensional boundary conformal Carrollian algebra. So the thing what here I want to emphasize is that because of the presence of the boundary for the open string, for the tensile case also we study boundary CFT. Here also we are going to study boundary Carrollian conformal field theory. I will show the.
I'm really sorry. So here you're talking about Dirichlet boundary conditions.
Yeah.
So, and the previous slide you were discussing Neumann, right? If I'm right, for the open strings.
No, here it is. This is the general mode expansion where nothing has been put. You see, there are tilde as well as C.
Okay.
If
But
we
upstairs there, okay, you allowed for both Dirichlet and Neumann, and you had a comment that was I right that for the Neumann you get an extra null condition, or is it?
I'm just saying that for tensile theory, if we have action and we vary that action, that has to become 0.
Right.
Then one thing is the boundary condition should be periodic. We get the close. In order to have open string, we have these 2 conditions. Okay?
Yes.
However, for tensionless case, we have these 3 conditions.
Oh, 3 possibilities.
Yeah, 3
it can
possibilities.
be Dirichlet, Neumann, or
Yeah.
Okay, now I understand. I see. And then in the next slide, you're talking just about the Dirichlet case.
Yes.
And that's because, and there are also correspondingly strings which would, open strings which would satisfy the Neumann or
And
the
null. However, we have not studied them.
Okay,
The
got it.
reason, one of the reason might be because this is the first work we have done on this. So we want to see whether we are getting the same result from the limiting side as well. So in the limiting side, we are starting with Dirichlet, when we are explaining later.
So now usually the Dirichlet correspond to deep brains, right?
Yes.
So in a sense, you're exploring the deep brain structure in your
Yeah,
But
What is this? The third condition? I'm not familiar with the condition.
Yeah, this condition we are also not very much familiar with, but I can show you that we are going to get this extra condition.
That condition also satisfies,
Yeah, we have to. So what happens generally is if we have certain action, then we vary the action.
Correct, the variational principle.
With the variational principle, then we need to make this 3 things 0 along with the equations of motion. So we got that.
I mean, I don't want to, sorry, please go ahead and you can just talk about it whenever you like, but I mean, in the tensionless limit, are we talking about massless particles from a space-time point of view? No, right? Just the entire Regge trajectory, is it? I mean, from the space-time point of view, what do you keep when you take the tensionless limit in terms of the excitations of the string? Just because then it might help put a picture together.
Can you just repeat it?
Oh, actually, I just want to ask the question, but you answer it whenever you like, which is there a physical, so let's say you had a string in the tensile case, and it has all the excitations, the massless modes, all the excitations, maybe they lie on various Regge trajectories, etc. Right? Now you take the tensionless limit, what part of the spectrum are you keeping? are you taking the because T is going to 0, are you taking the very high end of the spectrum basically?
So it generally corresponds to ultra high energy sector of string theory. And if we want to have some visual of this, that can be thought of as the collection of massless point particles.
They can't be point particles, right? Because since you go to the high energy limit, there'll be like floppy strings or something.
I think she means like an arbitrary high stability.
Okay.
Like spinning, infinite. It's like an infinite tower of spinning massless
Yeah,
particles.
Okay,
Because
go ahead,
where
please.
the length of the string is going to.
Okay. No, I'm just asking because the closed string sector was analyzed before, right? And there, is this right that it basically just becomes a collection of, maybe infinite number of non-interacting particles? Is that what happens? I see. Okay, that helps. Okay, so now somehow in the open string case, you're looking at the deep brain and you're putting this Dirichlet along all spatial directions, right? Presumably. I mean, are you putting delta x mu equal to 0 in your next slide when you do Dirichlet brains for the time direction also, or only for the spatial?
So the idea here I would be showing is that when we are putting Dirichlet condition to any of the space-time dimension, what are we going to get?
I see.
And that the result what we are getting there is similar to the one we will get if we go from the tensile and we put this tensionless limit and what we are going to get.
So you put Dirichlet on some and Neumann on the others?
Yeah.
Okay, that's what you meant.
Yeah.
Okay, so it's like D brains of different dimensions.
Yeah.
Okay, thank you. Got it. Thank you.
But in this talk, I will not be talking about D brains, just the construction of open strings and what the algebra are we going to get.
But for Dirichlet everywhere. So Dirichlet everywhere.
If we have Dirichlet in certain directions and Neumann in certain, that is also fine.
Yeah, but
If we have Dirichlet in all the direction, that is also
for the stuff.
Brains of any.
Yeah, including the instant answers.
Yeah.
Okay.
Okay.
Okay, thank you. And no supersymmetry or anything, right?
We will study later. Okay, so this is the idea about what are residual symmetries and what we are getting in residual.
Sorry, and Carroll means C goes to 0?
Yeah. It is kind of this limit, the other relativistic limit.
So Carrol means speed of light, C, worldsheet speed
Speed
of
of light
equal to
is,
0.
yeah. Okay, then I will talk about quantization. This has been done already, but this makes the audience very intrigued about how one can get from one classical theory 3 different quantum theories. So we are getting from here, we start with the classical bosonic closed tensionless string. We quantize it. When we quantize it, we are going to get 3 quantum theories based on 3 different vectors. I'll show how. Okay?
So in the worldsheet theory you chose, you can get 3 different vacua and they give 3 different space-time theories.
Yeah. But this might, so there was a recent paper, so maybe I'll discuss explicitly about it. And then I will talk what happens when we compactify one of the target space-time dimension. You see, for tensile case, when we compactify, so there is a concept called T-duality that comes over here, and the mass spectrum is given by this. However, when we go to tensionless, we don't have the momentum modes, so we don't have the winding modes, and you must be thinking, which is right, that the T-duality is lost here. I can give you physical interpretation of what is happening when I will go.
It seems somehow that when you take alpha prime to 0,
Exactly.
they get like infinitely heavy or something. It just takes too much energy to wrap around.
Right. Should it be that? Would you expect the other way around? Like it would be very easy because the tension is going to be.
Oh, I see. But alpha prime is going to 0 or to infinity. Am I mixed up? I'm sorry. Or maybe I'm mixed up. Alpha prime is going to infinity. No? Oh,
Yeah, alpha prime is endless, so it's going to infinity.
Yeah.
Oh, then you're right. I'm sorry. Yeah, that is
Yeah.
wrong.
Like infinitely.
Then why is it that you don't get any? It's
Let's
like-
say we have alpha prime over here, which is very now. So now what happens in T duality is we have one circle of, let's say, this is R, and another theory is we find on radius alpha prime by R. Now, let's say the radius, if the radius of compactification is very less as compared to the length of the string, then if this is very less as compared to length of the string, then this part dominates. Right? The momentum moves dominates. And the opposite thing happens when the length of the string or the radius is very less compared to the length of the string. Okay? I will be explaining.
I see. But okay, in your language, because you're calling, if I'm right, alpha prime like the length of the string.
Yeah,
right?
length
So it's
square.
r square over length square.
Right.
So why couldn't we take, since the length is going to 0, alpha prime is going to 0, oh, no, or infinity. I see, the length, alpha prime goes to infinity. But can't we take r fixed and alpha prime to go to infinity? In
Yeah,
which case,
I will do that. If we are fixing R fixed and we are varying the length of the string, which generally happens in tensionless case, the length of the string changes, we are going to get this particular form. I'll show it. Maybe I can just a minute, let me show you.
Sorry, but the bottom line is that you do get some kind of T-duality.
No.
Okay.
Just we want to. So this problem was stuck for 2 years because we were not getting T-duality. But ultimately we found that we are not getting T-duality.
So your thing seems to just break up into a bunch of point particles here, into a bunch of point particles.
it almost doesn't know that it's a string. Is that why physically you don't get the winding sets?
No, you should get the winding sector, right? You just get an infinite degeneracy or something. It seems like the winding direction is flat. And then it goes to a flat space. Like that.
Just wondering, given her result.
Okay.
So this is how, if we are fixing the R and we are changing the length of the string, from that perspective also we are going to get the mass to be momentum dominated.
By mass being momentum dominated, it just means that you have the winding sectors, but you ignore their contributions.
Yeah.
Okay, so it's like an infinite degeneracy
Yeah.
for each. Yeah.
Yeah, it seems like the order of limits is such, right? Like somehow that term in her language here is r square over L string square.
Yeah.
Isn't it more that you do have the winding sectors, but it costs you nothing to wind? Isn't that the correct?
Yeah, that could be the right way to the right mean of explanation, because we have very long
That's what you said, right?
So
Okay, that's more understandable in terms of what you focus.
So then why do you say that you don't have T2?
the absence of T-duality by that term I mean because what happens in T-duality is we have K and omega interchange, and that thing is not happening here. We don't see explicitly the term presence with omega. So in that way we can say we think in that way. I don't know, maybe that interpretation could be wrong, but
Say,
so he was asking that why am I saying that there is no T-duality?
Right.
So in T-duality is the theory defined on
yes, sir.
R and alpha prime by R, along with if we interchange the momentum and winding modes, we are going to get the same, that is the symmetry of the theory. However, we don't have that kind of thing in tensionless regime. So
So it's like you have you have finite radius and then you're taking the tension to zero. Then it's kind of difficult to wrap the like have momentum modes, but it's infinitely easy to have winding modes. So to reproduce the winding spectrum, you'd expect to reproduce it in flat space because then the momentum modes would be infinitely easy. But then there's no winding. Stuck.
Yeah, you don't have, I mean, if you went to alpha prime over R, that's some limit which is going to infinity. Yeah.
Yes.
So we
Yeah.
do
Yeah,
have
so I guess so you have to like come back to finite alpha prime and then talk about it.
Yeah, yeah.
Yeah. See.
But I mean, what couldn't I imagine like when I mean, your limit alpha prime going to infinity, you could also scale R appropriately to come to that.
Yeah, we can, but since it is going to infinite, so
Yeah.
Yeah, there could be some other
Double scale,
yeah,
double scaling limit.
interesting. Right, where R square scales like alpha prime, so R and alpha prime over R, right, whatever. Something
Something, yeah.
Okay.
Okay, then when we generalize this, so here what we have done is one space-time compactification. If we generalize to higher dimension and we introduce BC, there will be something interesting result on existence of some new corner of string theory.
Sorry to take it.
Yeah,
But
yeah.
just one last question about the winding thing. So you said this was equivalent to an ultra high energy limit of regular string theory, right?
Yeah.
So in that point of view, you should still have T duality. You just have, so you take a finite radius and then you take really high energy states. Shouldn't you be able to then get an approximate spectrum of this tensionless formalism?
So what happens after? So there is some concept called Heredon temperature, which is so this is the Heredon temperature, which is very high temperature. If the temperature reaches this Heredon temperature, there is this phase transition in the system, and there is this new degrees of freedom coming. So the string theory ceases to exist after certain limit, and we think that that is the tensionless limit. We speak.
When the radius of the circle goes very small, this phase transition.
Yeah, but for free non-interacting bosonic strings, we know what the spectrum is, right?
Why talk patent?
Okay, so this was like, okay, let's not think about it in this way. I'm just saying that this tensionless limit cannot be thought of as just the string theory at some at the end of some energy, but it is beyond something where some new degrees of freedom are coming.
You're saying, naively speaking, the Hagedorn temperature goes to zero in your scaling. Because the Hagedorn temperature is of order the string scale.
Yeah.
In energy, so you're sending that scale
Yeah.
to zero, right?
Tensionless. Yeah.
So, right, if I understand. So, in a sense, she says they're already past it and you're probing what lies beyond.
Yes. Yes. Yes.
I was asking because, in case there is such a limit in which you can realize the spectrum, so that would mean that you would have some kind of T duality where you map any finite radius to flat space. But since your tension goes to zero, you can kind of have long strings at finite energy cost or something because the tension is going to zero. So the winding spectrum on the finite radius side would be reproduced by the momentum spectrum on flat space, and the momentum spectrum here would be reproduced by these very long strings.
Yeah, that can also be thought of, but what I think about this theory is it is very near to zero also we are in the string theory regime. However, when we are just hitting that epsilon to zero, we are going to some theory which has something which is different from the string theory we know about.
This would be something that is not there, right? Like usually don't consider extremely long strings because if there's any tension at all, then the energy is
Yeah,
immediately
correct.
infinite.
Yeah.
Okay.
Yeah, we can
Just in case
think.
you ask.
Yeah,
After the deck.
we
I mean, there
we will talk.
Yes, they're describing the other field. And then just to, this is interesting. So in usual string theory, the number of states as a function of energy also grows linearly, which is why you have the Hagedorn transition, right? And in your case, let's just take the closed string, which is tensionless. How does the number of states or the entropy, say number of states grow with energy, space-time energy? Do you know? Because I'm curious. I see. Just to understand the thermodynamics of the beyond the Hagedorn phase, right?
So the number of states remains are infinite here.
Are infinite, but they should depend on the energy, right? Space-time energy. Usually, you know, for lower energy, you'll have fewer states.
Yeah. So here what we are getting is, yeah, you're right about it, because when we consider the oscillator's vacua, there we are getting infinite number. So we have the tachyonic thing, and when we compactify some space-time dimension, the number of tachyonic vacua or the number of physical states. Yeah, so this also happens here, that the states which are allowed, that also varies with some certain conditions. So not in, I would say there are not infinite number of states, but with certain compactification or something, we can allow few states which can be physical states.
Yeah, please go.
Okay, so here.
Just sorry, I really didn't direction. So, these take the closed string as you're describing here. These different vacua, do they give rise to tachyon free theories?
Here we get the tachyons.
Okay.
Here we don't get.
Okay.
Here also.
So we should not really take the oscillator vacuum too seriously, right? Because it's an unstable vacuum.
Yeah.
So, but in the other two cases, you have no tachyon.
No. And we are also getting something very interesting called Bose-Einstein-like condensation over there. I'll show that.
I see. So you have no worldsheet supersymmetry at all, if I understand, right? I mean, but you have, it's the analog of the bosonic string, but in the tensionless limit, and there you have the tachyon free string.
Okay, so in this way I can say that we have, in string theory, we have highest weight representations. And if we take tensionless limit of the string theory, the highest weight representation, we end up with getting the induced vacuum. Okay? And here all the states are massless.
States are massless. Very good.
And flipped we are going to get from the twisted string theory, which is a different string theory, which is related to the usual string theory by automorphism.
So in the middle one, you just have a bunch of massless because the tension has gone up to zero.
All of the perturbative states, they
come down.
Yes.
And it's tachyon free. And do you get any restriction on the number of space-time dimensions? Let's say you demand Lorentz invariance.
Yes. So for oscillator vacuum, we get the restriction to be 26. For flipped, 26. However, for induced, there are no restrictions.
No restrictions. I see. Interesting. And sorry, the flipped had no tachyons?
No. Even the level 2 is only physically acceptable states. I'll show how.
I see. The others are.
No.
But Okay, if you're going to discuss it, I see. I mean, the other levels are physically unacceptable in the sense they're not there in the spectrum at the end of the day, or you rule them out by hand?
We rule them out because of some constraints we impose on them. So what we do in usual string theory, we take the constraints, we impose on physical states, and then whatever we are going to get, those are the allowed physical states. So the allowed physical states for flipped vacuum is level 2, just one level. That's what I'm saying.
And these vacua are like independent. You can have either one or two. There's no inconsistency with not having the oscillator vacuum.
No, we can have, so from, okay, I can give you one simple analogy for this. Okay, so in usual string theory, you must be thinking we only have one kind of quantum theory, right? We have highest weight representation, we have one. And why are we having 3 different and how are they linked? Now, for usual string theory also, we are taking the constraint, which is the stronger constraint. If we make them weaker, then we will also get different quantum theories in usual string theory, which has been done recently.
Talk about the sandwich thing.
Yeah.
Okay.
So there also we are going to get some different vacua, some different quantum theories. What we are going to get it here. But when we take just the direct tensionless limit, we are going to make this induced vacuum. And induced vacuum is related to oscillator vacuum by Bogoliubov transformation.
So, okay, maybe that's true. Okay, please on.
So this is all about the main results I would like to show. Now I'll start with how we are going to get to that. So the idea is clear here, right? We'll start from tensile theory. From tensile, we know tensionless, the action we know. We have 2 different types of closed string and open string. Then we have the mode expansion. We put certain condition on mode expansion and we find out the residual symmetry algebra in both the cases. We quantize the closed tensionless bosonic string. We see the impact of compactification. We also see how B field tell us about the existence of some extra limit of string theory, which we don't know yet. Okay. So here we know that the tensionless action has Poincare symmetry. It also has the worldsheet diffeomorphism, which is an asymmetry. And since there is a gauge symmetry, we do gauge fixing V alpha to be V0. And this gauge fixed action still has a residual symmetry left, which the generators of this residual symmetry satisfy the algebra, which is the 3-dimensional Bondi-Mesner-Sachs algebra, which was in case of string theory, the Virasoro or the Witt algebra.
Okay, so you get the entire Virasoro, is that right?
Sorry?
You get one copy. You're describing the closed here?
I'm describing closed tensionless. And these are BMS3 algebra, super rotation and super translation. Yeah. So,
just sorry, I should be more familiar, but you get it without the central extension, or you're just writing the...
No, just the classical part I have written. I will write down the central. There will be central.
You just once say what is in terms of the space. That's what I think.
Yeah, I will explain them, but they are super translation and super rotation. I will explain them what they are. On the cylinder, they take this form. Right. But I will show what are they. Okay, so this from the action, we can get the equation of motion and the constraints equation. And in this gauge, it simplifies to this.
Oh, I see. There are no L till that, right?
No.
Oh, okay. So M's are roughly, I guess, the
No. They are.
I understand. They're not literally the other chirality, but there's some linear.
Yeah, exactly. They are linear combination. Let me write it down for you. These are the Virasoro. I will show we are getting this. So this is the equation of motion. This gives us the equation of motion, and these two are the constraint equation, which are the energy momentum tensor. The mode expansion which solves this equation of motion is given by this boxed equation, where V0 gives us the momentum, and for closed string, A0 has to 0, because it should not have the linear term. And yeah, A and B are the oscillators. Here C prime is this one, and the dimension is equivalent to the alpha prime dimension, which is the length square.
Oh, prime is C.
C prime.
Oh, that's C prime over E.
Yeah. So that's why the dimension of C prime is the length square. Now, if we will see the Poisson bracket of X and P, we will see the Poisson bracket of AB oscillator, what I showed you. They don't satisfy the harmonic oscillator algebra. Okay? So in order to get the harmonic oscillator algebra, we define new modes, which are the C modes, which I was showing you, which are the linear combination of A's and B's.
Just show the previous slide once more, that expansion.
This one?
Let's see, because here, I guess it's the A minus I in tau.
Yeah.
Is it different from the alpha means,
Yeah,
right? That's why you're not
Yeah.
getting the usual.
Yeah,
Okay.
here also it is different, and you see there are no sigma plus sigma minus associated with alpha.
Yeah.
It is.
Yeah. I mean, it seems that the tau dependence is just the linear. So really strange. Yeah. I mean, the tau dependence has just become linear, right? You're not. Like normally you get left or right movers
Yeah,
and
yeah.
so on. Here it's. I see. Okay.
So for that reason, if we define new modes in terms of C and C tilde, we are going to get the harmonic oscillator algebra. And the mode expansion of the constraints I already showed you, these T1 and T2, that can be written in this way. Okay, we do this for usual tensile string as well, where we find out the constraints and then we find the mode expansion. When we put this into the, when we put the mode expansion into the constraints, x dot square equal to 0 and x dot x prime equal to 0, we are going to get this.
These constraints are basically the equations of motion for rho and lambda.
Yeah. No, for V alpha.
Right. For the,
Yeah.
the analog of the stress
Yeah,
tensor.
These ln and mn's are expandable in terms of.
In terms of A's and B's, also since A's and B's are related to C's, so they can. Okay, so we can derive all of these classical results, like the residual symmetry algebra as well as the mode expansion, everything, if we directly take the tensionless limit corresponding to the tensile results. And the tensionless limit is this, the ultra-relativistic limit, which I was showing you. And this has been done by Bakchi and collaborator in 2015. And when we start, so we start with the tensile mode expansion, we put this limit onto it. Then when we compare it with the C oscillators mode expansion of tensionless, we get this relation, which is the Bogoliubov transformation. Okay. This is related. So C oscillator related to alpha oscillator by this relation. And this ultra-relativistic limit can also be seen in the symmetry algebra, which I've already looked at. That if we shape epsilon, the tensionless limit, we are going to get from the Virasoro, we can come to the BMS generator by this relation.
What was C and tilde? Oh yeah, those were your combinations of A's and B's.
Yeah. So the idea is we formulated something intrinsically, we got them from the limiting analysis as well. Till now, this is the idea. Now we go to open string.
Just to show that alpha, to get it, you take alpha prime to go to C prime over epsilon.
Yes.
And now what you do is you take epsilon fixed, keeping your nu, tau, sigma, and C prime fixed. Is that correct?
Can you repeat?
Sorry. From the usual results to obtain yours, you take in the usual result tau to become epsilon tau,
Yeah.
sigma to become sigma,
Yeah.
and alpha prime to become C prime over epsilon.
Yeah.
Then you take epsilon to go to 0, keeping your nu, tau, sigma, and C prime
Yeah,
fixed.
yeah,
Right?
yeah.
Okay. Got it.
Yes.
Yes. Thank you.
Now I'll talk about open strings. For open string, I'll just give a brief review of what tensile open strings are. So string theory, we have closed string. The worldsheet is like cylinder. For open string, we have infinitely long worldsheet. The action is same for both of them. And the boundary condition here, the closed string is given by the periodicity condition. The open string has this Dirichlet and Neumann boundary condition along with in order to make this variation of S.
Really sorry. Just to understand, so you said that the spectrum becomes that of just a bunch of massless fields, and presumably for arbitrarily high spin, right? In terms of space time.
Yeah.
So you get
Yeah.
arbitrarily high spin or massless. Okay. Thank you. Sorry.
So from here, could you just go back to the equations of the function? Sorry. Right. So the x double dot mu equals 0 is true at every value of sigma, right?
Yes.
So it's like every point on the string is like an independently moving particle, roughly speaking.
Yeah.
But what is x? Can you physically, what is the x dot x prime equals 0? Is there some physical way to, I mean, it's sort of not completely independent because of this condition, I suppose. These particles are not totally independent.
So these are the constraints what we get. So you want to know
I mean, I was wondering whether there's some physical picture. You can't literally think of them as being independent because of this constraint.
I see. What is T1 and T2? Just to understand, in the limit, tensionless limit, what are T1 and T2?
So these are the energy momentum tensors we get.
Okay. So just definition, in
Yeah.
a sense. But the operating equation is x dot x prime equal to 0. Okay, yeah.
Yeah.
So your point is you can't literally.
Yeah,
there's a
They are
prime
not
there which
completely
connects.
independent, however.
Okay, good point,
No.
good point. Yeah, that's.
Okay, it's not a problem.
Yeah, because x dot square equal to 0 is the massless condition,
Right.
so that we understand.
Right.
X double dot equal to 0 is a
Right,
bunch
right,
of free
right.
particles. I see. What is the second?
The second one seems
Good
interesting.
point, good point. Yeah. I see. Interesting.
It's roughly like it's like saying this particle doesn't move in the direction along.
I think they are
move
tied to
perpendicular
each
the-
other.
Right. I mean, if you're nearby particle, there's
Yeah,
some-
kind of this null necklace kind of
doesn't want to
thing.
move in that direction. It's to move. But
The second equation.
yeah, the middle equation. I think that's sort of an interesting.
Yeah.
Thank you.
It's very good. Okay, thank you. Interesting. Okay.
Yeah, so we have Dirichlet condition and Neumann condition. Now, what does they mean? So let's say we have this rule and we have Dirichlet condition in this Z direction and we have Neumann condition in this surface. Then the end points of the string, they can move on this surface, however, they cannot move in this direction. That generally means what do we mean by Dirichlet condition? And I will be talking about Dirichlet condition, but the important point is for Dirichlet condition or Neumann condition or any condition for open string, we see that the left moving modes and right moving modes are related to each other. So that means now the two copies of Virasoro what we were getting will go to single copy of Virasoro. Same thing, if we do for tensionless open string, we have to start with the ILS reaction. And this is the boundary condition. And you can see that we also have to make this part 0 in order to have in order to make the variation of action 0. So along with Dirichlet and Neumann, for case of tensionless strings, we also have this null condition. We have not explored on this more. Maybe this will give us some exciting results, but the gauge which we are considering is not very good to work on this null condition for the moment. So we will be talking about this Dirichlet condition. The equation, the mode expansion of the null open string is given by this. The way we find out the mode expansion. And here you can see that we don't have any tildes over here. We just have one kind of a symmetry.
I should have asked you this before, but V alpha from the worldsheet point of view is a space-like. What kind of a vector is it? V
It's a
alpha,
vector density.
No, it's a vector, but you had it in component form, right?
Yeah.
Some component was big and some was just once.
Depends on the this.
Okay. One and rho.
And when you gauge fixed it to something, right?
Yeah, 1, 0.
Lambda is just some.
Lagrange multiplier.
Just to. Okay,
Rho is also.
Rho is also.
It's
Then you have to integrate over them. So now depending on their values and blah, blah.
No, I think she just gauge fixed it one comment.
I gauge fixed it to
1, 0.
in
Oh,
constants.
there. Okay. And this is time, the first component. is
Yes,
time.
yes.
So you have some null n dot time. So it's purely along space. Your third condition.
Yeah.
Okay. Thank you.
The way that condition enters, it's like the middle condition that enters in the mode expansion.
This one?
No. In this mode expansion. Is there some signature of that condition, the x dot x prime equals 0?
X dot x prime.
That's one of your constraints, right? Oh, you haven't imposed it yet.
No.
Oh, you have.
Yeah.
Yeah,
So
that's
this
why
is just the
the
mode
mode expansion
expansion.
just looks like it's a bunch of free parts.
Yeah,
Every
and
n there's a
that
free part.
there I have imposed this Dirichlet condition, just that. And then there are these constraints, and these constraints will give us the algebra, which is the boundary, variance boundary. This is also exactly equivalent to the case we do for usual string theory or the closed string, where we find out these constraints and the generators of this constraint. So here the generators, they will have relation with the C's in this way.
So you have a bunch, so that's why you have a bunch of free particles, but these constraints make them into a string.
Yeah. That could be thought of as the necklace, what we are trying to study now, that are they like this constraint, are they keeping them together?
Somehow they're-
Yeah. Is it the case? Okay, so these are the boundary conformal Carroll algebra we get. So this was the two-dimensional conformal Carroll with the central extension, with the central term. Okay, and this is the for open string, and here we get the boundary conformal Carroll algebra. Now the generators of which will give us this two-dimensional boundary Carroll algebra, and the generators which will give us two-dimensional boundary conformal Carroll algebra are different on such a basis that, let's say we have this null cylinder and we impose some boundary to it. So the generators now will break this symmetry along the boundary. The translation symmetry across sigma equal to 0 and pi are lost here. So imposing that condition, we are going to get the, so if we want that kind of boundary condition, then there will not be any term which will have del sigma in it. So these are for 2D conformal Carroll. For open string, we have O and P. For O and P, we need to satisfy this boundary condition that there should not be any symmetry across the boundary for sigma equal to 0 and tau, 0 and pi.
First of all, why are we talking about null cylinders and so on? I mean,
So since this is the BMS, so when we talk about tensionless strings and when we talk about its residual symmetry, that we are going to get the BMS algebra, which is the two-dimensional Carrollian conformal algebra, which is the null asymptotic limit of the flat space.
and just like normally the Vera zero is just diffeomorphisms on a circle,
Yeah.
let's say, and this is what is sorry to be so poorly informed, but this algebra what keeps the structure of square plus or something intact. Is that
So
what is it?
So we have circle as well as the, so we have a cylinder on the square plus and square minus.
And it's a
And the circle, on the circle, the super rotation is given by ln, and mn gives us the super translation, angle dependent on.
this R is to be thought of as an algorithm.
Yeah.
I'm with you. Okay.
So for the boundary, so how these generators are different from them is can be seen here, that they will not contain this kind of terms, which will keep the symmetry intact across the boundary. So here the translation across the boundary is lost. So we won't have the terms like del sigma in our generators, which will be in ON and PN. Okay. If we construct the generators in that way, we are going to get the symmetry algebra to be of this, which is a new algebra. And the contraction from the BMS, we are getting it. This is the contraction. If we follow, then we end up getting ON and PN. ON and PN are the generators for open string constraints. Okay. And the global subalgebra is this. For tensile case, it generally gives SL2R. Here it is 2D Poincaré ISO 1,1. Yes. So all of this can be seen from can also be retrieved from the tensile. If we take this limit, with the ultra-relativistic limit, we can go to the null open string expansion with this Gogoly-Vogt transformation. And the summary of what we did till now is that tensile string theory, we study 2D CFT on the worldsheet. When we go to open string, we study the 2D boundary CFT. Similarly, when we go to tensionless string theory, we had 2D conformal field theory, 2D Carrollian conformal field theory for closed. When we go to open string, we get 2D boundary Carroll conformal. Okay. So this is all about the classical analysis of tensionless strings till now. We discussed about the closed, we discussed about open, we discussed about some of the residual symmetry algebra. Now we will go to quantum analysis, where we will see that from one classical picture, we are going to get the three different quantum theories. So in classical sector, we have seen that the components of energy momentum tensor vanishes, T1 and T2 vanishes. However, when we quantize the theory, these components are promoted to operators. So we cannot just make them vanish. Okay. So what do? We demand all the matrix element of the operator in the physical Hilbert space to vanish. So this is the constraint we are going to use. And since in T1, as I showed you earlier, that T1 has this ln as well as mn, so we have so this can be written in terms of ln and mn, which are the generators of these constraints. And since there are, okay, so the constraints, the sandwich condition can be satisfied by three possible conditions. Okay. One, the highest weight. Second, let's say this is 0 for all, n not equal to 0 for all of them. And the third, let's say the highest weight, the right hand side action is not zero, however, the sandwich is zero. Okay, so this is the weaker of all constraints. In usual string theory, we only consider this part, and hence we have only one theory. When we consider the weaker constraints as well, we will get other theories.
But not in the usual bosonic case, right?
Yeah, even in the usual bosonic case, now there was one month, few days back, there has been one study by Jabbari and Arjun, who showed that it is possible to get different quantum theories if we consider the weaker constraints.
What's the weaker? Normally we do impose it weakly, right? That ln on physical states for n greater than 0 is vanishing, not all components of ln, etc., etc.
They are saying that there's a more general class of states which satisfy this physical condition, which comes out in the end. I mean, what you want in the end is what you said, right? The physical ln physical equals 0, and they were trying to show that they showed that a more general class of states than the one we usually see in textbooks satisfy this condition. But I thought they weren't relevant in usual string theory, and they become relevant when you move to thermal, like a regular boosted worldsheet or something, so that you get this Bogoliubov transformation, which leads you from the regular spec. But okay, that's their paper.
Yeah.
So
just the idea is we are going to consider not only just the highest weight, but the weaker constraint as well. Weaker in the sense this is non-zero, but the sandwich is 0. If we do that, now we have ln as well as mn in our constraints. I showed you here. We have ln as well as mn. Since there are two possibilities, so we can have 9 conditions which are considered 9 conditions which can be considered as the quantum theories. However, if we want them to be consistent with BMS3 algebra, then we only get these 3 conditions, which will give us 3 different quantum theories. The flipped one is the highest weight. The induced is the induced representation of BMS algebra. Oscillator doesn't come under any representation of BMS. However, it is related to the induced by Bogoliubov transformation. So this results in 3 different quantum theories on 3 different works. This has been studied by Pandit and collaborator in 2020.
Did you have central extensions in your theory?
Yeah, we will.
Then how can you impose ln equal to 0 for all n, not just positive n? I mean, in the oscillator case, doesn't it seem?
the central extension has C in it. That's what I meant.
Their C is not going to 0, right? You have a Vira 0 with a central extension, right?
Yes. Sorry.
No, non-zero central extension.
Yeah, so.
I was just wondering, because normally in usual string theory, you have to impose the Vira 0 constraints weakly, right? Because, the algebra has a central extension, so how could you impose it strongly, right? Etc. So I'm just wondering here, your third one seems.
Yeah, he's saying take the third one, take ln, take l minus n. So if both of them acting on physical states give you 0, then the commutator should also give you 0. And if you have a non-zero C, then it looks like it doesn't give you 0. So that's again how it's consistent.
So I guess C is.
Yeah, I thought you full string.
So we
I'm confused. You said no, you had non-zero central extension, or
yes, I showed. But for the oscillator, if you want to see, this is how we construct the theory.
AL is 0, M is 2. And M and no, wait.
So maybe ln is not quite, but ln on physical states maybe is some constant.
This gives us the level matching condition, or this gives us the L0 condition, gives us the allowed, which physical states are allowed. L0 condition gives us that.
Is that also true of M? I usually say
M gives us the mass spectrum.
No, but are you also imposing that Mn acting on all physical states is 0?
I'm acting this Cn acting on the vacua will give us 0, and on this, I'm going to build up the states. Sorry, I think I cannot understand your question.
I'm just asking, rephrasing Sandeep's question, which is,
Mhm.
can't you use some linear combinations of Cn's and C tilde n's to get Ln and Mn?
Yes,
Uh,
we
so-
used that.
So if you would go back one slide.
Yeah.
So in the third condition, you apply Mn acting on all physical states. Oh, it's not 0, but the sandwich is 0.
Yeah, yeah.
But then if you have two Mn's, then it's not 0. Not necessarily. So okay, so
No, but
physical
then
state Mn.
our physical state will differ, right? So only allowed physical states are the one which are level matched.
Yeah, but also like physical state Mn physical state is 0, but physical state Mn prime physical state may not be 0.
Yeah,
Correct.
yeah,
So,
yeah.
Yeah, it's fine. I think just go back one slide. The second equation, Ln is not 0, right? Ln does not annihilate. So I don't think there's a contradiction with the extension.
I'm sorry,
We
it's
got
not
out of
equal to 0.
Oh, you thought this is equal?
No, I thought, I really apologize, I see.
Yes,
You
yes.
don't autocorrect it.
I'm so used to seeing the conditions with
That is
equal
for
to
this.
this. Okay, then of course it's fine, I guess, but you somehow meet the required whatever conditions you have. All right, sir.
Shall I? Yeah, so this oscillator vector, I'll just give a brief introduction to what they are. So the physical state condition is given by this, which is the weakest of all, and the Lorentz invariance that demand that AL is 0 and AM is 2. And this suggests, and the vacuum on which this theory is constructed is the oscillator vacuum defined in this way. We define it in terms of C and C or tilde oscillator. In the mass spectrum of the level match states, so why am I saying it is level match states? Because this is coming from the L0 condition. And the mass spectrum is given by equation 16. It tells us that we get tachyons. Okay, because AM equal to 2. And the vacua is tachyon. Okay, then the induced vacua. If we take direct tensionless limit of the usual string theory, we get tensionless strings on induced vacuum. And the physical state condition you see here is this is sandwich 0. However, Mn acting on physical state is 0 for n not equal to 0. So here we can see that all of the states will annihilate because n is not equal to 0. This is 0. And the induced vacuum is defined as the direct tensionless limit of the tensile vacuum, which is given by Bn on the vacua is 0. And if we have 0 momentum, then B0 is also 0. However, when we find out the action of M0 on this
So these
vacuum,
BX were the same oscillator as that.
yeah. Shall I write down the?
No, that's okay. Right.
Yeah. So Ln, just one thing, Ln are like A and B combination. Let's say M minus 1 and Mn as both Bn this. Okay. So here we can see that since AM is 0, B square acting on the M0 acting on this, which will give us the mass square. Why I'm saying this is mass square? Because B0 is coming from, so M0 will give us mass spectrum. M0 means we will get one with positive N with Bn, and the other one term will be B0 square. Okay. B0 square will also give us 0, and which is the mass of the vector. So
Sorry,
this is
AM wasn't 2.
aim.
Not 2.
Aim was 2 for oscillator case.
Okay. Okay.
I'm sorry, I have to.
Yeah, yes. So here I am showing this, that all the perturbative physical tensile state condense to the induced vacuum, resulting into a worldsheet. Bose-Einstein-like condensation. You can think of it as that these are the usual tensile string spectrum, and these are just
The usual tensile string spectrum has a tachyon. I guess
Yes.
that also goes out
Yeah,
to zero.
yeah, yeah.
So in that sense, this doesn't have tachyon state.
In that sense, yeah, we can think.
Why are we calling it a Bose-Einstein transit?
All like Bose-Einstein-like condensation. Like all of them are going to
You just have design
condensing.
say, right? You don't
Yeah,
have-
yeah.
Okay.
Yeah. And that can also be they in their paper in 2019 paper, they have also said this as the closed strings spectrum going to open string, because there is this. But that analogy, I think,
Sorry, closed tensile going to open tensile, is closed
Oh.
tensionless going to open tensionless? Or?
yeah.
Okay.
But we haven't found any relation with what we have studied, that open tensionless case with theirs. But they do give this analogy that might be here all of them are since going to the just one vacua, so it might be like it is the tensionless open strings, or the space filling d-branes also they call it. Okay, so the flipped vacua. So this is the constructed on the flipped vacuum, corresponds to the highest representation of BMS algebra. This is the strongest condition, the right-hand side action. And here demanding Lorentz invariance results in AL equal to 2 and AM equal to 0. This was also done in 21 by Bakchi and collaborators. And here one thing has been changed, that like here we have the holomorphic and anti-holomorphic. For anti-holomorphic, this has been flipped. So C n tilde on vacua is not 0. However, C minus n tilde on vacua is 0. And there is the tensile analog of this theory, which is called the twisted tensile string theory, discovered that has been studied by Lee, Rosabal, and Casali and people. Here, the physical state condition imply that only level 2 state is physical and they are massless. This I was saying earlier. Okay, so when we compactify one of the space-time dimension, that means we have winding states, winding modes, and because of this compactification, there is change in. So let's say we compactify x 25th direction in d equal to 26. Dimensional theory. So that will change the zeroth mode of A0 and B, zeroth mode of A and B, okay, which will contain the winding modes and the momentum modes. And that will change the zeroth modes of C and C tilde oscillators. Why I am showing all these? So zeroth modes are important because that will change the mass spectrum. Okay? And the mass spectrum we are going to get is given in 19. So in all of the vacua or all of the quantum theories, if we compactify one of the space-time dimension, the mass spectrum will gain one extra term, which is k square by r square. However, for the tensile theory, it gains this whole term, which we already discussed a few minutes ago. And if we understand this, this can be thought of as momentum dominated and winding dominated, and which are related to each other by some T20. When we compactify more than one of space-time dimension and we introduce B field, I will say why am I saying that we have to compactify more than one space-time, target space dimension? Because for B field, we need to have compactified dimensions. Otherwise, we can't introduce B field. I will show you how. So this also, we start constructing it from the usual tensile action with B field. And then we do the same replacement. Here we have done for T root Z, G alpha beta, V alpha V beta, and B mu nu as B mu nu by epsilon. in order to survive this. And then we are left with this action, which is tensionless action with B field. Now, since we are working with the constant B field, so it does not affect the equation of motion, the symmetries, the residual symmetry algebra, as well as mode expansion. However, it will affect the canonical momentum because there is, so in the B field, you can see that there is del alpha, so it will be, so this is antisymmetric, tau and sigma, that means the x dot and x prime will be there. Equation of motion will not be affected because that is double dot. Here it will be, the canonical momentum will be affected. Now, if we find out the total momentum, you see, we can only get the non-zero B field if we have compactified dimension. If it is not compactified, then x sigma plus 2 pi will be equal to x of sigma, and this particular term will vanish, and we will only have this left. So we need to have compactified dimension in order to introduce B field into the theory. And since we have this compactified dimension, so we have this total momentum. Let's not go into very detail of it. However, I just want to say that this also changes the mode, the zeroth modes, because of which the mass spectrum changes, which is given by equation 25. Now, if we do the quantum analysis, we also get 3 different quantum theories. And for all of them, this mass spectrum remains same. You see that we have k square term, and where this can be written in this particular form. We have k square term, we have omega t, omega square term. So you must be thinking that, okay, if we introduce B field, then might be there is possibility of having the T duality. Is it the case? We will see. So this can be written in terms of matrix notation in this way, where G is a generalized metric of the double field theory. What is double field theory? Double field theory tells us about the, so in double field theory, we have both the coordinates as well as dual coordinates, which generally manifest this T duality and ODDZ symmetry very explicitly. So we get that kind of theory with something called degenerate inverse metric, which is given by this. So the form we are going to get is of this form. However, when we go to tensile theory, we also have this kind of generalized metric, but we have, the form is a bit different. This is the form we are going to get. Here extra G is there and all others are same, like B, G inverse B. And in this slide, I'm showing that if we take the tensionless limit, this given in 28, we are going to end up getting this particular mass spectrum. Okay, now the symmetry of the mass spectrum.
I'm confused. Why is scaling B with the tension but not G?
Okay.
So the B field you're scaling with the tension, right? It was in the,
Yeah, this one.
yeah, this is 1 over epsilon.
Yeah.
But you don't have that in G.
So when we construct the action, in order to make the action, so in order to keep the B field in the action with the tensionless limit, we have to scale B in certain form. So I have just shown this there. Yeah.
But you don't have to do that with G.
G, I think, somehow implicitly.
Because that would take us back to your double scaled thing, I think, and then you would have T.
Yeah. Right.
You are asking me that why we don't have to scale this G.
Mm-hmm.
So just G. So first of all, what is this G? This G is the metric on the torus.
This is R.
Yeah.
Connected to it. The root of my confusion is just that I feel like you can get this from a high energy limit of regular string theory, and that doesn't feel like there should be a problem with the commutation between that and duality. Like you could.
Yeah, I got it. But yeah, we generally don't scale this R.
Okay.
Okay, so here also, if we have tensile string theory, in the presence of B field, we get ODDZ symmetry. The symmetry of the T duality is enhanced to ODDZ symmetry. What is this? This consists of basis change, discrete shift symmetry, and factorized duality transformation. There are a bunch of transformation which combines to give us ODDZ symmetry. Now we want to see what happens when we go to tensionless regime, whether this symmetry exists. But what you are saying, if we are scaling R, then we can also get this symmetry.
I don't see the math immediately, but I feel like maybe.
Oh, yeah.
Yeah, maybe.
It's intuitive.
So the basis change can be think of as, let's say K goes to some CK and omega goes to some. So these are some basis change transformation. The mass spectrum remains invariant, not that important. Discrete shift symmetry, if we shift B to B plus N, that also the mass spectrum remains invariant. However, if we have some factorized duality, what do we mean by that? So let's say we have two of the space-time dimension compactified. Okay. Now we have K1, omega 1, K2, omega 2. K1, omega 1. K1 is the momentum mode for R1, we can say, the compactified dimension, and K2, omega 2 are the modes for the R2 compactified.
You essentially want to invert the metric you wrote down before, right? The two field.
Which metric you are talking about?
So this is the analog of R going to alpha prime over R.
Yes.
So you essentially want to just invert the metric that you wrote down earlier, and now it's degenerate. So
yes. So this factorized duality means, so one of the duality means there is inversion duality where all the K will go to K1 will go to omega, omega will go to K, all of the Ki's. However, factorized means, let's say one will change and all other will remain same. If we do this kind of transformation, for tensile case, we see that the theory remains in the tensile theory regime. However, when we do this for tensionless case, we are not getting that one, we are getting some theory which is not staying in the regime of tensionless case. However, we are thinking that maybe that can come by some other limit of tensile theory. This is shown in that way. So let's say this blue, oval shape region gives us all the theories which can be explained by Polyakov action. Okay. Now there we know that there are T dualities, there are S dualities. So where the theory from one theory can be connected to the other. They are dual to each other. We know that. Now let's say we have two theories, A and B. They are related to each other by some factorized duality, as I showed you. One of the K and omega are exchanged. Let's say here we have tensile string with B field. We have tensile string, we have introduced B field, and we have T2 with diagonal metric GIZ. The torus is given by GIZ metric. Now that is dual to factorized, that is dual to theory, which is without B field, okay, with different metric GIJ. I can show you this by showing. Okay, first let me finish this and I will show you that. Now, when we go to tensionless regime, so let's say there are many corners, there are other corners as well. I have just shown two. So let's say all of this theory will have certain theory, when we take this tensionless limit, and it will go to, let's say, this corner. Now, this A is also going to this corner, this B is also going to this corner. But when we are taking this B to this corner, and we are applying this factorized transformation to it, we are getting some generalized metric, which is not of the form of what we have started with. Okay.
So you think it's not your tensionless limit, it's some
Yeah.
other limit. Which...
Yeah. It might be that there is some other limit which we don't know, which comes in some other corners of string theory. And yeah, so this seems to be very interesting to us, that it might be some other corners which we are getting.
Can it be a point particle limit?
It might be. Okay, so this is all about what I wanted to say. Now there are some future directions.
But there are only two ways to take the limit per string theory that you started showing in the introduction, that you can take either tension to
Those are extreme limits.
Yeah.
We can have, for example, here, the metric is becoming degenerate. So that may be some other limit which we don't know.
Can you please go back 2 slides to the metric expression? Yeah, this one. Yeah, the one after.
After this one?
So here, if you, so B goes like 1 over epsilon, right?
Yes.
So if G also goes like 1 over epsilon, then you won't see the degeneracy, right?
If G also goes,
Like 1 over epsilon.
so B goes like 1 over epsilon. This,
Or
yes.
alpha prime also.
This is G inverse. So G inverse you are saying goes like 1 over epsilon. So alpha prime has epsilon C prime by epsilon.
No, I think I was being too careless. So alpha prime also, if alpha prime, so I was thinking maybe if you take G, B, and alpha prime, then you
Everything
can get
equal.
non-degenerate metric.
Okay. As far as I remember, that was not that
I see.
tricky to find out if we are getting.
Okay.
Yeah, so this study with boundaries, because Carrollian limit has been a lot in discussion now. So Carrollian conformal field theory with boundaries should help us explore more topics. And Carrollian CFT are at the heart of flat holography. So this means that if a flat version of ADS BCFT correspondence would involve the symmetry. So what I mean by this is ADS BCFT correspondence is there. So we have flat BCCFT correspondence. We can. So I told you something about this degenerate limit of double field theory. We can think about it more if that can give us to some interesting result. And we also notice a subset of ODDZ symmetry. Subset means the factorized duality, which might possibly connect the tensionless string to some other limit of string with degeneration. So it will be exciting to have intrinsic analysis of other limit, what I was talking about, in order to confirm this condition. So this.
I have to leave my question.
Yeah.
One quick question. So, for instance, in the tensile string theory, I guess there's a standard beta function calculation one does, and but when you introduce like a space-time and target space metric or other Dirichlet and so on, the beta functions give you equations of motion from the space-time point of view. So here, have you guys explored
No.
tensionless version?
That part has not.
But there, the logic behind the beta function calculation is confound and variance on the worldsheet.
Yeah, so I was wondering what the analysis
Yeah,
here is,
same.
right? And in particular, do you get local? I mean, my main question was, do you get a local equation? An analogy with the like, is there some like tensionless version of Einstein's equation? So I would expect it to be somewhat non-local.
Okay.
Anyway, thank you.
Yeah, I mean, you would also expect more than this G and B to be there.
Yeah, I guess I don't know, maybe everything gets done. You could, yeah. I mean, in that sense, it would be presumably. I mean, you get, I don't know, maybe some higher spin equation.
That will be a convenient way to pack in.
Yeah, yeah. I mean, if there is some, it's not. It would be terribly. I think it'd be very interesting.
Yeah,
There's
yeah.
some
Yeah.
convenient way to answer this package them. Like, these Vassiliev equations are very complicated and right?
Yeah.
Maybe your beta function.
Yeah, but there was this study by Gross and Mende that when we go to extremely high energy limit, all these scattering amplitudes become very simplified. There are relations between them. We have not explored that. We will be exploring that.
And have people looked into how scattering works in tensionless string?
Yeah, so Gross and Mende, 1982, I would say they have worked on it, and they said that in this regime, the scattering amplitudes, we have infinite number of linear relations, and hence that becomes very simplified, telling us about this high presence of this high, extremely high energy sector. But in this way, we haven't.
Do you have anything to say about
Non-perturbative, yes. So all the perturbative, so what I have in literature till now, we have this perturbative states going to the massless induced vacua, but not much has been studied on non-perturbative states.
Okay, so it's time for Priyadarshini again.
It was very nice.
Thanks.